In this video, we're going to check out some very cool properties of the definite integral. I'm going to use geometry to explain why the properties make sense so that you're not just memorizing random facts. Here we go. I'm giving you the definite integral from a to b of f of x is equal to r. So what does that look like? You've got some function f of x here on the graph from a to b, and r is the area of all of this right here. Ignore c for now. So, couple of facts here. We're going to use this space to understand. What would the definite integral from a to a of f of x dx be? Well, if the area from a to b is equal to some number r, some constant r, this would be saying what's the area from a to a, which is saying that we never actually accumulate any area. We just stay here. So we'd have no area at all. So anytime you have the same bounds here, these are called bounds or limits, your value is going to be 0. That's it. We don't accumulate any area at all. This next one says, what happens when you reverse a and b? So instead of integrating from left to right, you're integrating from right to left. Well, what that would do is it would completely flip your delta x, if you will. You end up with the opposite r value. You end up sweeping out area this way instead of going left to right this way. Think of that as like going backwards in time. So if we move forwards and we go up when we move forwards, then when we go backwards, we must move down, right? And that's the idea here, the opposite value. The other way of looking at that is you could say this is the same as the opposite of a to b of f of x dx, and that rule will come in handy. All right, next rule. We put C here for a reason. What this basically shows is that the overall area from a to b between f of x and the x-axis could be split up. We could start at a and stop at c, and then start back up at c and keep filling in the area until we get to b. So the idea here is we can split up a definite integral at any x value between a and b and add those two definite integrals up, and it will sum to the whole area. In basic terms, if I've got the area of this part and I add it to the area of this part, it gives me the area of the whole thing. That's all that says, right? So these properties are very simple when we look at them with geometry. All right, how about from a to b, where you have 8 times f of x dx? Let's take a look at that one. Well, what's that all about? Well, we've got the integral from a to b is normally this. Now we're taking this and multiplying everything by 8. I wonder what that means if we multiply everything by 8. Well, remember, these are the heights of rectangles. You're taking this curve and making every point on it 8 times as high. So then the area is going to be 8 times as much, 8 times r. Now this also extends to mean that we could have not evaluated, but factored the 8 out to start with, evaluated the definite integral, and then multiplied by 8. That's all that we've got right there. So it's not so bad at all. Very, very cool. And on this next page here, I've copied that part over to show you how it makes sense generally as well. So if we take a look at this whole thing right here, 8 is just like k. Now we already knew that that would give us 8 times r, and that we could factor out the 8, that's what we just looked at on the last page, from a to b of f of x dx. The same thing then makes sense for any constant. I just wanted to use a number first. So in general, if I multiply the function by any constant, then our overall area will be k times r. Or, probably the more important part there is that I could take out that constant first and then evaluate the integral. Now we'll see this rule come into play down the road, but this is a very simple idea. It's just like when you take the derivative of something, like if you're taking the derivative of 3x to the 4th, the 3's chilling out, you handle the rest of the derivative, and the 3 hangs out. It's just like with the k. The k's hanging out, handle your business right here, and then multiply by k. All right, last but certainly not least with all of this, and some of this kind of fell off the screen here, but this is the a value there, and that's the b value there. I've given you now 2 functions, a function g of x and a function f of x. And the question becomes, what happens if I add or subtract f of x and g of x? Well, what I can then do is I can split up the integrals. I can write it as the integral from a to b of f of x dx plus or minus the integral of a to b of g of x. It's plus or minus because it just depends on what it was that we had for a sign to start. So what does this say in terms of area? It basically says that if I'm adding or subtracting the two functions, my result will either be the sum of the two areas if we're adding them, or the difference of the two areas. That's it. So if I were to take these two things and combine their curves, I could still separate them into two separate curves, find their individual areas, r and s, and add them or subtract them. So these are very simple rules backed up by geometry. You're going to want to know these rules. Do you have to memorize the geometry? No, but you're going to be using these rules enough. Specifically, I'd say the most important rules, being able to factor out a coefficient anytime, you'll still get the same area, still get the same answer, as well as this idea, if you have the same bounds, we're equal to 0, and this, but especially number 2, will come up a lot. So that if you have switching of bounds, you have a switching of signs of your area. That's all. We're going to put this all to the test and see how you do with this with some pretty neat textbook-like problems that I've made up, and we'll do that in the next video. Can't wait to see you there. Peace.